We thank Amazon Web Services Educate, AWS Educate program for generous support via donated cloud computing credits. Hello everyone. We are here in this video to present our final PowerPoint presentation for EE599 Deep Learning at USC Viterbi School of Engineering. Our project is titled Designing Interpretable Approximations to Deep Learning with Soft Decision Trees. So the motivation behind our project: neural networks are everywhere, they are ubiquitous. However, their explainability and interpretability is a problem that hinders their adoption in safety critical systems like autonomous vehicles and aircraft, where safety and predictability are paramount. Therefore, analyzing their behaviors over all possible inputs is an important but open problem. There have been some attempts made, but it has not been conclusively answered. In this project, we are really interested in deep reinforcement learning. It is the most interesting algorithm for control tasks. For example, Google's AlphaGo and the Atari games were played using deep reinforcement learning. We seek to create interpretable architectures for deep reinforcement learning tasks. So the interpretability will be done by approximation by decision trees, either hard or soft decision trees. In a hard binary decision tree, it returns a firm output. In that case, our action is just a control action A. In a soft binary decision tree, however, the leaf node has a vector of probabilities associated with every action, and you choose that action which has the maximum probability. Literature shows that soft binary decision trees have less complexity but better performance over control tasks. So within one slide, this is what our project aims to do. So on the top, you see a conventional deep network sort of a setup. What we aim to do is to remove the deep neural network and replace it with a decision tree policy. It will be a verifiable and interpretable approximation of deep reinforcement learning.
In order to do the mentioned approximation, we borrow ideas from imitation learning, wherein a student policy is trained by trying to imitate the expert policy, which in our case would be the DQN network. One of the earliest attempts at imitation learning was behavioral cloning, which is to generate state action pairs from the expert and to apply supervised learning. But this approach makes an IID assumption and has been shown to be suboptimal. We therefore use a more recent result from imitation learning called Dagger, which stands for dataset aggregation. This algorithm takes into account the trajectory which would be followed by the student policy, and it's an iterative procedure which rolls out the student policy in every iteration and queries the expert for the actions which would be taken over those states. These state action pairs are then appended to the existing data set, which is then used to relearn the student policy. In our setting, the expert is the DQN policy and the student is the decision tree. And we are training the decision tree using the Dagger algorithm.
The decision trees that we use in this work are based on those of Frost and Hinton. They represent a middle ground between decision trees and deep neural networks in that they have hierarchical decisions, but the parameters of these decisions are trained via batch learning. So specifically, each internode learns a filter and bias, which is applied to the input that generates a probability of taking either the right or left branch of its output. Each leaf node then, as was said earlier, learns a distribution over the possible actions taken, and this entire tree structure is trained based on a weighted cross entropy where the weights are based on the probability for a given input of arriving at the leaf node L. So our first case study was applied to the cart pole problem. This is a reinforcement learning benchmark problem where the goal is to keep a pole upright, which is attached to a cart, which can be moved left or right, as seen in this video. We trained the DeepQ network that achieves this performance. Note that it takes about 38,000 trainable parameters to characterize this network. whereas our soft decision tree can be trained with just about 50 parameters, and also can balance the poll up to the maximum 200 time steps, which is interpreted as solving the problem. This is the picture of a hard tree that would describe a policy, a hard tree policy. For this task, notice that the decisions are made based on individual state attributes. So for example, the first decision is made based on whether the pole is tipping to the left or right, positive or negative, and subsequent decisions are also made based on, for example, velocity or position of the cart. So in the context of our soft decision tree, you can see that the decision is made based on a sequence of binary decisions. You can see we have mapped the inputs for element state to colors, and the input state is multiplied with the learned kernel, and based on whether or not the output of that multiplication plus the bias is positive or negative, the binary decisions are made as it traverses down the tree.
The next case study we come to is the mountain car problem. As you can see in the figure, the goal is to reach the flag post over here on the hilltop using an underpowered car. So the best policy would actually be to reverse and then go ahead. So in this case, the state space is continuous with two states, the position of the mountain car and the velocity. The action space is go left, go right, or do nothing. You have to complete it within 200 time steps. For every time step that you don't complete, you get a -1 point penalty. Once again, as was the case with the cart poll, we generated the decision tree for the mountain car. Again, you can see that kind of classifies it using separate cuts of state space. So in the at the root, it asks whether the car velocity is positive or negative, and then subsequently it takes some branching decisions and arrives at a leaf where it returns some action. Coming to the soft decision tree regarding the mountain car problem. So this is the soft decision tree, and the green arrows indicate the direction taken by the tree. Given that there are only two states, purple and yellow, every node learns a filter and a bias. So the corresponding activation is computed. If it is negative, it goes left. If it is positive, it branches towards the right. In this case, you see it branching left, left, left. At the leaf node, you see a vector of probabilities. The action that is most favored in this case is the go left action because it has the highest probability. So that is what is returned by the decision tree. So this is how it looks. If you use a DQN based controller for the mountain car, you can see that it succeeds as a task. And this is how it looks when you use first the hard decision tree and the soft decision tree. You can see that both of them complete the task, but the hard decision tree based controller is somehow more aggressive, qualitatively speaking, which we will see in more detail in further results. So this is called as the state action diagram. So you take all the possible states, so all the possible positions and all the possible velocities, and for every position velocity ordered pair, you plot the corresponding action generated by the DQN. So this is how it looks for the DQN. We did it for three other cases: the hard decision tree, soft decision tree with behavioral cloning, and the soft decision tree with Dagger. You can see for yourself that the bottom right diagram, that is soft decision tree plus Dagger, comes the closest in terms of approximating the DQN action. The other result we found was the effect of the tree depth on the ability of approximation. So we did this for the hard decision tree. Decision tree of depth 3 could not approximate the DQN policy really by much really. A tree of depth 12 came really close to approximating the DQN policy. The other analysis we did is the phase portrait, so-called, or it is also called as the action trajectory diagram. So you see these spirals, they evolve outwards with time. So they start at the center, the origin, and at every point in time, what we do is we plot the position, velocity, and then the corresponding action. Again, we do this for the DQN, the soft decision tree with behavioral cloning, the hard decision tree, and SDT plus Dagger. You can again see that the SDT plus Dagger comes the closest in terms of approximating the DQN. The hard decision tree, however, is much more aggressive, as I had pointed to before, because it completely misses this orange region, and that is why it looks just like a bang bang or an on-off controller. So this is a video of the mountain cars with different control algorithms. All of them are played together. The last analysis that we wish to show you is the statistical analysis. So the red colored curve is the cumulative reward versus episode number for the deep Q network. So we simulated the mountain car for 100 separate episodes. We recorded all the cumulative rewards and then plotted it on a graph. So the red curve is for the deep Q network, blue one is for the hard decision tree, and the green is for the soft decision tree. So in this case, you can see that the hard decision tree is much more biased. It is much more rigid in terms of decision making. Compared to that, the soft decision tree has considerably more variance for the same tree depth. So we used hard as well as soft decision trees with 3 layers in them. And you can see that the soft decision tree already approximates the deep Q network much better than a hard decision tree does. So finally, the hard decision tree needs much higher number of parameters to allow accurate reconstruction of the DQN policy. The soft decision tree had just 46 parameters compared to a DQN policy of 14-19 parameters. In spite of that, it succeeded in all the episodes. It did not fail in even one episode.
So let me give a quick conclusion to our work. We approximated the deep RL policies in terms of decision trees, hard and soft decision trees, by the use of imitation learning algorithm called Dagger. We tested this on 2 case studies, the cartpole and mountain car gym environments. We also further noticed that soft decision trees are able to capture greater detail than hard decision trees with greater training accuracy on the expert data. So we believe that this implies that soft decision trees would be able to perform better than hard decision trees, more complex state and action spaces. Thank you.